Okay, hi Nidir. So we are going to talk about superposition of waves in this chapter 13. There are a few topics left, so we'll try to cover them through videos a little bit quickly so that worksheets go through as we are planning. Okay, so let's jump into this chapter. So we are going to learn about superposition. I don't know if you have heard this word before, so we are going to get into that a little bit more. So let's see. So every wave looks like goes up and down, right? So let's see. So every wave goes up and down, and then this keeps changing. Like right now it is here. At some point later, it must have moved a little bit. So then it kind of looks like this when it has moved a little bit, right? And this is fine. Like the wave is moving like right to the right in this example, and this is fine. It happens. This is called a traveling wave. That the wave is traveling along the plus x direction, and that's fine. This we understand. Now, what is a superposition? So this is one traveling wave. We want to superimpose waves. So there are multiple waves because there is an S here. So there will be multiple traveling waves which will be superimposing. So a question like this arises. Say you have a wave that comes here and is traveling to the left. Then you have another red wave on the same thing that starts from the other end of the pool. Right? So imagine there's a big swimming pool. You are creating waves at one end, and then this guy's creating waves at the other end. And then what happens at the point in the middle, right? So, of course, you might imagine that okay, while this will travel, okay, it will move forward, then it will reach here, right? And then this point, this will come here. The blue wave will come here. So this is okay, this is stable. But then it moves further, and the blue wave then will want to take this particle to move down, right? And the red wave will also move the particle down. So the particle will start to move down, right? So we have to add up the behavior of the two waves in a way, right? So let's see. So this is what happens. So say there are two waves. At this point, you see that both of the waves are kind of working together, and then we have to understand that, right? So let's say one wave is the blue wave and another wave is the green wave. Both are smooth, but we see that okay, at this point the blue wave wants to move up, and then the green wave also move up. So as a result, it moves this up plus this much up. So A plus like B, which is this point. But say at a point like this where blue is 0 and green is still positive. So red value is just the value of the green one, and then you move a little bit further, then green is still positive, but blue all of a sudden becomes very negative, because of which the red becomes negative, and then you have this weird thing that red looks like, right? Which is, so we can call this the superimposed wave. Because of blue and green sources, we see something like a red. This we call the superposition, right? So you should definitely try this on your own. Try to follow two waves and see what is the red line that you'll get here. Try to do this in your, like, try to pause the video and try to do this. Okay, then this first concept, so this is one concept that we understand, superposition, right? So the next concept is diffraction. This chapter, you only need to understand a bunch of terms. There'll be 5 terms or something that you'll need to know. So first is superposition, second is diffraction, right? So what is diffraction? Diffraction is really simple. So diffraction can be understood like this. Let's forget about all of this. Let's see this example. So what you're doing is, there is something that is creating vibration there, and then there is a solid wall here. So let me replicate the setup for you a little bit. So there is a wall here in this, and then there's something that's maybe creating oscillation there. So maybe like something like, maybe you're dipping the finger, or maybe there is a ball that goes up and down inside the button creating wave. So the question is, what happens in this area, right, in the X marked area? So what they say is, if this D, it depends on the D here. If this D is big, then the waves continue to go more or less straight. Now, but the crazy observation is that when D becomes small, very small, the waves actually become very spread out very quickly, and instead of going in a straight line. So they kind of look like this. So earlier they were very going straight, but when the hole becomes small enough, they become very round circles, and then they start going outwards. So it's like, if you're standing So you tell me this, okay? So you are now, let's just, so you are in a room, okay? You are in a room, okay? Someone is making sound, so it's waves. Now the question is, you are this person Y that's standing right next to the wall, right? So the question is, will you hear the person, right? And the answer is, you will hear if this D is comparable to the lambda here. So if this D is roughly on the order of lambda, then the diffraction will happen, and then the sound will spread everywhere. But on the same end, if you consider this, that if say this was light, which has a much smaller wavelength, and then you have light up room here, and then there is a small slit here, right? So you imagine that the light will go nearly straight. So a person standing here where you are at that X mark, will he see the light? No, he will not, because the lambda of light is very small. So this D becomes now not comparable to lambda, but much bigger. D is say of the order of a meter, or like say if it is a door, then like maybe a couple of feet. But like lambda light is on the order of nanometers, as we had seen in the previous chapters, right? But for sound, this is not the case. Sound is also on the orders of like a few feet or a few meters or half a feet. Because of the thing that are comparable, there's this phenomenon called the diffraction happens, where waves come on a D source and then they spread out very fast. So this is one more concept that we have to understand, right? So this is called diffraction. Your book, so one example that here they say is very interesting. Like inside the microwave, you have microwaves, and the question is, why don't these microwaves come out? So the answer very simple, that the wavelength of microwave is 12.5 centimeters, right? And for it to come out through these holes, right, it needs these holes to be of 12.5 centimeter. But are they 12.5 centimeters? No, right? They're like half a centimeter, or like even lesser, like they're 1 centimeters or 0.1 centimeter, like very small holes. Now lambda here is much bigger than D. So in this case, no diffraction will happen. They can't even go out. So it just reflects back, right? So this mesh at the start of microwave is very important. We don't understand it, but then this, because of this reflection phenomenon, it's very important, right? Okay, now the third term, interference. Okay, we'll keep moving like this. As I said, it's just a bunch of terms that you need to understand in this chapter. Interference. So interference is nothing but, it's like superposition only. It's just when two things are like interfering or adding up to each other. So it's something like this. So you have two waves, right? So both are same waves. So the blue and the yellow are overlapping here. So if blue and yellow are overlapping, then the red just is like, okay, both blue and yellow want to go positive, so this also goes positive, right? So this is called constructive interference. When both the waves are helping the red rise up, and then when both of the waves are helping the red go down, then both of the waves are helping it go down. Then this other case is possible when they are destructively interfering, meaning that when this tries to push it up, this tries to pull it down. As a result, the red is bang in the middle and it does not move at all, right? So this is interfering with each other destructively, and this is interfering with each other constructively. So it's essentially just superposition, but when we are specifically here talking about two waves, right? So you can also have interference between waves of a different amplitude, right? So it looks like this wave only, but here they are still constructively interfering, right? They're both helping at the same point, and then they're both helping negatively at the same point. They always work in what we call phase, right? So let's discuss that a little bit more. Okay, right. So something like this. So we say that in this case there are two waves with different frequencies. So you see the wavelength here is still here, and this one has a longer wavelength, or we can say in terms of frequency or wavelength. So they have different wavelengths. So at this point, both of them are helping. So this also wants to rise, this also wants to rise. But if you see at this point, then green wants to rise, but blue wants to fall. So at this point, they are out of phase. And this point, they are in phase. right? So when they have a constant phase difference, so we see that here they don't have a constant phase difference, right? Phase difference is changing. First it is in phase, then it is out of phase, and then it is in phase. But in something like this, it was always the same because the wavelengths were same. This is always helping, always helping, always helping, always helping, always helping, right? Helping means it is the same direction, right? So this is called coherence. When both the waves are working in the same phase, they have a constant phase difference. If the phase difference here was 0, then here it is 180. So this phase difference has changed, right? Right? So phase is the difference between the two waves. So this is they're in the same phase. This is they're out of phase, right? Okay. Then let's talk about this concept called path difference. Right. So one thing that we saw in here was constructive or destructive interference that you need to know. And then the last thing that we heard about was phase, in phase, out of phase, which we extended to have a form. So we can say that two sources are coherent or not, right? And the last thing that we need to see here is something called path difference. So let's see what that is. Okay. So path difference, what does it mean? So it's saying that, okay, if I have a wave, right? And if I have another copy of that wave, right now, if they constructively interfere, if I overlap them, just one on top of the other, then they would constructively interfere, right? Like what we had seen. Okay, now let me do one thing. Now this is when path difference is 0. Okay, so let's just call it p, not lambda, just to avoid confusion. This is when path difference p is 0, right? Now let's say that, okay, I shift this like I shift this forward by one wavelength. So instead of starting at this point here, it's starting at this point because one wavelength is shifted. So it's like this. And then I interfere them. Like then I make superimpose them. So part difference here is lambda, and the red line still looks the same, right? Because it really doesn't matter. Like in this area here, more waves from the back will come. So it will just look like the same thing that you're interfering, right? But let's look at what happens when you just shifted by path difference equal to lambda by 2. That means you have only shifted by half the wavelength. So your the yellow point has moved to this new yellow point. Now let's see what happens. So now it says that yellow, this is at the peak, but at the same time blue is negatively at its peak, right? So at this point they're destructively interfering, right? So similarly we can understand that if it were to move by lambda by 2 plus another lambda, so half a wavelength and then full wavelength forward, which is 3 lambda by 2, it would still be destructive interference, right? So from here we understand that for all these it is constructively interfering, and for all of this it is destructively interfering, right? So the idea to understand here, the key idea here is, if the path difference between two waves is equal to n times lambda, then it will be constructive interference. If it is n plus 1 lambda by 2, sorry, 2n plus 1 lambda by 2, so that means if you try putting a different n here, so in the first case when you put different n's, you get 0, you get 1 lambda, you get 2 lambda, you get 3 lambda, you get 4 lambda. So these are all just wavelength shifts, right? So they will still constructively interfere. But in the second case, if you put n equal to 0, then you get lambda by 2. Then if you put n equal to 1 here, then it becomes 3 lambda by 2. Then it becomes 5 lambda by 2. That means that it is shifting in that one half a wavelength plus one wavelength, like that. So these will be destructive interference, right? If you don't understand it, pause it and rewind the video and just like make sure that you get this idea properly. So this path difference idea is very important. So how much should you move one? And of course, if it's not an exact multiple, then weird things happen, right? Like what we saw. Okay, but these two cases are important when the exact thing moves. Okay. Now extending this idea about of interference to something we call YDSE, or Young's double slit experiment. Let me repeat that, YDSE. Right. So Young was the name of the experimenter who had first done this double slit experiment. Right. So what he saw was something like this. So he said that if we had one hole, right, we saw that whatever waves are coming in, they go outwards, right, in a circle. This is fine. This is diffraction. Now what he did was made another hole in the wall. We said that will also produce waves, and what will happen? You know where I'll go with this. So one is producing waves like this. The other one is producing waves like this. Now the question is, what will happen in the yellow area in the middle? Right? So what will happen is interference. What will happen is superposition. What will happen is these two waves will interact with each other, and one wave might try to push it up, one wave might to push it down. So we have to see what will happen. So let's analyze this in a little more depth. What will happen? Okay. Okay. So same setup. Let's look at the point that's bang in the middle, like divided by half, right? So the number of waves that have come here and the number of waves that have come here, like how many wavelengths are there if you count, and then how many wavelengths are there if you count, they will be exactly the same, right? So the path difference between them will be zero, right? And when path difference is zero, we know that they constructively interfere. So that means if there is some light here, right, that's coming out, this will be what we'll call a bright spot, right? Because it is constructively interfering. Now, if you move this point a little bit down, right, move this point to a new point, say B, then you see that okay, like maybe I can have half, like some extra wavelength here, and then maybe this, because this lower path becomes a little bit smaller, maybe a little bit less here. So maybe the path difference here will rise now here, and maybe it becomes lambda by 2, which is some number, right? At that point, you will have a destructive interference. So this will be a dark spot, right? Destructive interference. Then similarly, if you move further down, right, you will have again, this will be having a little more path difference. The upper path, the green path, the blue path will have a little less again. And maybe you get to a bigger path difference, which is equal to lambda. Like the gap between those two is increasing, right? Then this will again become a bright spot. So when you start to look at it, it will form something like this. So a bright spot, big bright spot in the middle, and then a dark spot here, and then a little bit brighter spot here, and then a dark spot here again at D, then a little bit brighter here. And you see that they get a little bit dimmer towards the end. Like this is the brightest spot, and then so you see a pattern something like this. So A is bang in the middle, A is bang in the middle, then you go to B when it is dark, then C where it is a little brighter, then D, and then E, and then F, and so on and so forth, right? So this is part difference of lambda, part difference of lambda by, so lambda by 2, then lambda, then 3 lambda by 2, then 2 lambda, then 2.5 lambda, and so on and so forth, right? So this is the thing to understand. So this is what he saw for the first time, which was interesting. So a pattern like this, so bright spot in the middle, then little less bright, then so forth, and so on and so forth, right? Bright, dark, right? And one formula that we found from this is, if you want to find the wavelength of the light involved here, so wavelength of the light will be now a function of all of this. So if this distance of separation is A, and this is capital D, the distance between the screen and the slit, right? So double slit experiment. So because these are both slits, and then this is the screen, and then if you observe this distance X, sorry, from peak to peak, from A to C. Right, so let's check that whether it's A to B or A to C. X, they say that distance of adjacent bright fringes, right? So A to C, right? So X times A by D. So this is the formula that he found. That the wavelength of the light can be calculated using this. So if you measure the distance between two bright fringes here, and if you know this D distance and if you know this slit distance, then you can find the wavelength of the light involved. Which is so you are measuring something in nanometers through measuring something which is in maybe like this in a few centimeters, and maybe this is also a few centimeters, and just by and this is in a few meters maybe. You can measure something that is in a nanometer, which is great. Nanometer is very very small, right? Right. So this they can use to find. If you want to find a wavelength of an unknown object, you can do this. So you have a source, then you have some single slit which has some diffraction pattern, and on the end of diffraction pattern you add a double slit. The double slit will produce interference here, and then you can measure uh, the bright dark inside this region. Again, here it will only be bright, here it will only be dark. Inside this there will be bright dark bright dark. Sorry, both are bright here. And inside this they are bright dark bright dark. Between two brights, if you find the distance x, you know this distance a, then a into x divided by this big distance d will give you the wavelength of this light involved. Right? Okay. If you don't understand anything, just go through that slowly and it is fairly straightforward. Okay, so the very last topic that we talk about here is called a diffraction grating. Now it's the simplest extension because, so let's talk about it. So diffraction grating. So this concept essentially happens when we saw that there are two YDSCs, two slits in YDSC. Let's create another slit. Let's create another slit. Let's create another. Let's create a lot, or like 100 slits. Let's create. When you create such a thing, you have a diffraction grating. Grating is like a mesh. So this is like every one of them is like a slit, right? They work like a slit. So this is the idea of diffraction grating. So what happens is something very similar. You have a so bang in the middle of the diffraction grating, you will have a nice bright pattern, and then you will have smaller patterns. Like the pattern is still the same in a way. So here, if you have, say you're measuring at an angle theta from this, and the slit distance here is d, then we have this relation. Like if you are measuring the nth, this is n equal to 0 peak, this is the n equal to 1 peak, this is the n equal to 2 peak. So again, similarly, this is minus 1. So what the relation that was found here was, it looked something like this. So d sine of theta is equal to n times lambda. So say you're doing it for this one, you will do, say this is theta 1, so you will say that d, which is constant, which is the gap between the spacing in the diffraction grating. So d sine theta 1 is equal to lambda. Or you can say for n equal to 2, this will be theta 2. Then you will say d sine theta 2 is equal to 2 times lambda. Right? And then again, so similar thing is happening as YDSC. It's just like more than two sources now are interfering together to create something. So you have a grating full which all creates this n equal to 0 to 2 and further beyond patterns, right? And that's the key formula right here. Right, and because all of this is lambda dependent, the ratio. So like if you see here, like this theta 1 at which you will see a peak is dependent on the lambda, right? So if the lambda is higher, then this theta will be a little bit higher. If maybe lambda is a little bit, so if one is for 600 nanometers, one is for 700 nanometers, this gap will be a little bit different. So you will see that maybe the red, which is of a different wavelength than blue, so red will peak first and then the blue will peak. So what happens is, even though there is complete white light on this side, you will see that all the colors separate out on this side, which is the interesting thing about diffraction gratings. So if you look at this, like you have white light here, but then The blue peaks in first because it has the smallest lambda, the purple and the blues, and the reds have the longest wavelength, right? Always remember this. So they'll go out, they'll show up on the highest part. So you have colorful at the end, right? So you have, so these kinds of colors are all, so these are reflective diffraction gratings. So you throw light on them, what comes out is or is diffracted light. So this acts like a grating, which is why you see reds here, and it's because the angle that you're viewing it from, that is theta for one point, and then it is theta, a different theta for that, for some other point, right? And that same theta shows you, so this is constructively interfering for red. At the same point, those two things are it is destructively interfering for red, but constructively interfering for blue. And that is what like you can see from here. So whenever you see colors reflecting off like that, there is some kind of grating that's involved. So if you look at your phone, sometimes if you have bright light in your room, and if you look at this surface, like you will see that the light spreads out a little bit, like you see different colors. All of that is due to diffraction gratings. Okay, so that's mainly what I wanted to talk about here. So again, the main concepts here are diffraction grating, interference, YDSE. Interference means specifically constructive, destructive interference, being in phase, out of phase. What does it mean for two waves to be coherent? The path difference, and that we used to use. Do you do YDSE? And finally, like as we talked about, the basic superposition of waves, right? It's fairly an easy chapter. Just need to know the names. Just go through the internal examples, and you should be good. But make sure you understand all of these terms properly, and that's an important thing. You give the chapter a good read, and you should be good to go. Okay, see you later. Bye bye.